All right, so continuing on here with section 16.4, we have looked at what happens to our change of potential when the path is parallel to the field. Now let's look at not parallel. Okay, so as you might have understood by looking at that formula, this is still easy to calculate. I mean, after all, we are very used to working in 3D, so we're just going to move it into the third dimension. And also, we can kind of see indicated by the formulation, which is just a dot product, exactly where this is going to go. So let's say we had some path, A to B. We have our electric field going this way. So A is at x1, y1, z1, and B is at x2, y2, z2, and delta L is equal to delta x, delta y, and delta z. And so delta V is equal to minus E sub x, delta x, plus E sub y, delta y, plus E sub z, delta z. And this is basically just a generic dot product. So delta V minus E dot delta L is equal to minus EX, EY, EZ dotted with delta X, delta Y, delta Z. And there you have it. That's all we have to do. It just means we've got 3 components instead of just 1. So let's do an example. All right, so we have B at minus 0.3, minus 0.10 meters, going to A, 0.500, and our electric field has a little bit of an angle to it. So it's at 740 and 0 newtons per coulomb. And from A to B, let's calculate potential difference. So we'll do it for delta U alpha and delta U minus. Okay, so delta V, for that we're going to need delta L. This is equal to minus 0.3 minus 0.1, 0 minus 0.500, giving us a delta L of minus 0.8 minus 0.1, 0. And so delta V, strange delta, but it'll work, is equal to minus E sub x, delta x, plus E sub y, delta y, plus E sub z, delta z. Delta V is equal to minus 700 newtons per coulomb times minus 0.8 plus 40 times minus 0.1, 0. And so delta V is equal to plus 564 volts. Okay, so now we're all ready to do the drag and drop. Since we have our formulation for electric potential in terms of delta V times the charge. All right, so for alpha, delta U is equal to plus 2E times delta phi is equal to 2 times 1.6 times 10 to the minus 19 coulombs times 564. And delta U alpha is equal to 1.8 times 10 to the minus 16 joules. And then for the mu minus, delta U is equal to minus E times delta V V is equal to minus 1.6 times 10 to the minus 19 times 564 volts is equal to minus 9.02 times 10 to the 17 joules. All right. So let's do some more examples. Suppose there is an electric field equals 175 newtons per coulomb. If you move 4 meters at angle 62 degrees, what is delta V? All right, so if you'll recall, delta V is minus E dot dl is equal to minus E delta L cosine theta. Delta V minus 175 newtons per coulomb times 4 meters cosine of 62 degrees, which is the trig formulation of the dot product. Delta V is equal to minus 329 volts. All right, so we can use delta V to calculate fields as well. So delta V is equal to minus E sub x delta x. Or you could rewrite it and say that E sub x, the field in x, is equal to minus delta V over delta x. And it would follow for all of the subsequent components. So, for example, a capacitor has large plates 2 millimeters apart, and delta V is equal to 172 volts. What is the electric field? So, or the magnitude of the electric field. So the electric field would be equal to minus 172 over 2 times 10 to the minus 3 is equal to 8.6 times 10 to the 4 volts per meter. All right, so delta V, very useful, and also something you have been hearing terms in terms of voltage ever since you've talked about circuits. So, all right. Now, for the classical class, there is a calculus expression which actually more accurately describes this delta V. So the limit of a very short distance, E sub x, so E sub x is equal to minus the limit as delta x goes to 0, delta V delta x, which is minus dV dx. And this is called a gradient. So this is called the gradient. We do actually do gradients quite a bit in higher level physics. So you'll see it in advanced mechanics, advanced electromagnetism, quantum mechanics, really common. But in this class, I'm just going to introduce it. So the electric field is the negative gradient of potential. So E sub x is equal to minus del V del x. So you take the derivative of potential with respect to x, and then you repeat the process for y. You take the derivative of potential with respect to y, and then E sub z is equal to minus the gradient, or the partial derivative with respect to z. And partial derivative basically means you're just taking the derivative with a particular, with regards to a particular variable. So partial derivatives are used all over physics. Nice thing is they're really, if you can take a regular derivative, you can take a partial derivative. All right, so we often write this as E is equal to minus nabla V. So this little triangle with the vector over top, this is nabla, and this just represents taking the partial derivatives with respect to x, y, and z to find the x, y, and z components. By the way, physicists tend to write a vector sign over nabla. Mathematicians do not always. So just an example of just some different notation between the two fields. All right, so let's do a quick example. So there's in a region in space, the potential can be expressed V equals 4xz plus 2y minus 5z. What are the vector components of E? At x, y, z. All right, so E sub x is equal to minus del v del x, which is 4x. E sub y is equal to minus del v del y, which is equal to minus 2. And E sub z is equal to minus del v del x, or del z, which is minus 4x plus 5. And so our vector expression is minus 4z minus 2 minus 4x plus 5. There you go. Pretty simple. Okay, so moving on to 16.4 and thinking about the sign of delta V. So delta V can be positive or negative, and the sign determines if a particle will gain or lose energy. All right, so if the direction of a path is the same direction of the electric field, so we've got A going to B, and in the electric field 400 0 0, so the electric field's going in the positive x direction, and so is our path. Then delta x is going to be equal to 2 minus 1 meters. It's equal to 1 meter.